Okay, let's get started. Good day, everyone, and welcome to our webinar on decarbonizing combustion and steam methane reforming, which will be presented by Tim Talon of AMETEK Process Instruments and James Cross from AMETEK Land. My name is John Kearney. I lead the product management team at AMETEK Process Instruments, and I'll serve today as the moderator for the session. James and Tim are both excited to share some interesting and educational information on trends in global decarbonization that are driving the need for greater efficiency and tighter emissions in steam methane reforming. And they'll talk a bit on how to optimize combustion and utilize thermal imaging to improve operational efficiency, increase process safety, and lower emissions. Before I turn the presentation over to Tim and James to introduce themselves and share their content, just want to cover a couple of housekeeping items. We are recording the session, so just ask to minimize any background noise, please keep your phone or your computer mic muted. James and Tim would also welcome questions during and after the session. So you can use the Q&A feature on the Microsoft Teams platform. For those who might not be familiar with it, if you look up towards the top right area of your screen, you'll see a question mark and a Q&A box. You can just click on that and type in your question, and I'll be fielding those. I will interrupt James and Tim during the session so they can take questions sort of live on the content that's presenting. So definitely feel free to post any questions there. And as I mentioned, this webinar is being recorded, and we will be posting it on the AMETEK Process YouTube page in the coming days. The webinar is sponsored, obviously, by both AMETEK Process Instruments and AMETEK Land. Process Instruments is a worldwide manufacturer of process analyzers and instrumentation, and we serve a wide range of markets from environmental monitoring to hydrocarbon processing, including things like refining and petrochemical, as well as power gen and natural gas and many others. Land is a world leader manufacturer of monitors and analyzers for industrial infrared, non-contact temperature measurements, combustion efficiency, and environmental pollutant emissions. And Land serves very similar markets in steel making, glass making, minerals, hydrocarbon processing, and thermal power generation. So with that, I will turn the presentation over to Tim and James.
Thank you, John. Well, good morning, good afternoon, good evening, and thanks for joining us. We're excited. James and I are excited to share with you some perspectives in thinking through how do we prepare for the hydrogen economy, and in the process, how do we think about decarbonizing combustion in the combustion process and the steam methane reforming process. So thanks for joining us, James.
Thanks, Tim. Yep, I'm James Cross, Global Industry Manager for hydrocarbon and petrochemical industries at AMETEK Land. So excited to give my perspective from the AMETEK Land portfolio, generally relating to temperatures in this case. So thanks for letting me join, Tim.
Yeah, we appreciate your help, James. All right, so now just to give you an overview, as I mentioned, now this is really to provide an opportunity to talk about a combination of solutions that really provides safety and efficiency as we think about decarbonizing steam methane reformers, both inside and out. And in this agenda, we'll talk about global trends that are driving the need for greater efficiency and tighter emissions. We'll talk about optimized combustion, what it is, and how does it decrease emissions while also being able to monitor for safety. James will also dive into thermal imaging and the steam methane reformer tubes, tube wall temperatures, and how monitoring can also provide a mechanism for safety and also for higher yields. And then we'll talk about the combined Land and AMETEK Process Instrument solutions to really provide an overall picture for your plant, for your steam methane reformer, for safety and higher yield and reduced emissions. As John mentioned, feel free to ask questions in the chat or in the Q&A, and we can field those questions real time. There will also be time at the end for questions. So now just to get started, we'll talk about global trends. And I think the biggest thing about decarbonization is that there's a driving need in recognizing a need for climate control. And so how can both governments and corporations do their part to reduce greenhouse gas emissions, reduce global warming, and in the process, how do we think about reducing carbon dioxide emissions? Now, many industries will continue to require the combustion process, because of its high energy density for power and for heat. And so there are a number of industries, including steel, cement, and chemicals, that are relatively hard to decarbonize, as well as mobility solutions like ships and airplanes and air traffic and automotive that will continue to require combustion for their high temperatures and for their high density per energy content. So that being said, as we look to large scale decarbonization on the variety of combustion mechanisms out there and the variety of combustion processes out there, some that come to mind are carbon capture to directly remove carbon dioxide emissions from combustion, both before and after the combustion process. There's also electrification to generate heat in place of combustion. And then there's also using high hydrogen fuels or hydrogen as a fuel to generate heat without creating any carbon dioxide emissions. Now, that being said, combustion remains important in our future in our movement towards decarbonization, and that's partly why we're here to talk. I'll kind of pass it over to James real quick to speak even more about decarbonization on SMRs.
Thanks, Tim. So zooming out a little bit, just talking about the transition from grey to green. It's a discussion we've had extensively within AMETEK. So the end goal clearly is to get to the green space in hydrogen production as more hydrogen is produced for mobility applications, especially. But in the interim, there's obviously a huge demand from industry for hydrogen, and that's where we probably see the 20 to 30 year need for this blue phase of hydrogen. So that's switching from the current grey phase where dominantly SMRs are used without carbon capture and storage to a point where the CO2 is captured from the SMRs so that we can reduce the total carbon intensity of that process. So the industries that we tend to work in, fertilizer industries, methanol production industries, and the refinery supply of hydrogen for refinery processes like hydrotreating, cracking, etc. We see obviously a huge transition to blue hydrogen, and a lot of new projects are employing autothermal reforming with carbon capture and steam methane reforming with carbon capture. So one of the discussions we had was, how do we frame the systems and our experience in terms of decarbonisation? And the immediate steps is on both grey and blue hydrogen steam methane reformers, so that we can really help to increase the efficiency of those processes. And then obviously longer term, we're looking at how we can also support the electrolysis process, but we're a little bit away from that. And frankly, there's enough need for us to help with the blue hydrogen and grey hydrogen processes for now. So the energy transition generally is focused on migrating to those hydrogen fuels. So we'll talk a little bit in the longer term about how hydrogen firing is affecting steam methane reforming, but we're generally talking about natural gas fired burners and combustion processes today. So there'll be a lot of partnerships for blue hydrogen production. Green hydrogen production costs are coming down longer term. But what we're really talking about today is the existing assets. So the focus on efficiency, flexibility, and the safety of those assets, and what you can do to reduce the oxygen set point levels in those furnaces without risking the safety. There's reduced flaring on a lot of plants, which means that a lot of these previous waste gases are being redirected to headers. So there's more flexibility needed on a lot of fired heaters now. Carbon capture obviously is a longer term emissions reduction strategy. So efficiency gains is where we're really focusing on. That's what's in your current control, and that's what we can influence in the real short term.
Yeah, thank you, James. And really, as we move towards the hydrogen economy, and as we move towards increasing demand for hydrogen as a fuel source and as a globally overall, the Steam Methane Reformer is the backbone, and in the present industry right now in the installed base. And the biggest thing is, like you said, James, how can we think about efficiency right now to further reduce emissions right now within the operator's control? And so this is just a typical steam methane reforming process. And as you can see, it certainly starts with the hydrocarbon feed with some hydrogen recycle, getting some desulfurization and purification before being mixed with steam, going through a pre-reformer, and then into the steam methane reformer. And after that, certainly becomes syngas, carbon monoxide, and hydrogen before it gets purified and through pressure swing absorption. And I only do that really quick and briefly, but I wanted to highlight just from the typical diagram that really the steam methane reforming process requires combustion to maintain the proper temperature of these reaction tubes. And James, I know that you have some insight, especially on the different configurations that you wanted to comment on.
Yeah, sure. So I think over the years we've developed quite a lot of experience on all the various types. So obviously, and I'll talk about the licensing names. They're not secret to anybody. So there's a lot of Haldor-Topsoe side-fired furnaces out there. There's a lot of Foster Wheeler terrace-fired, multiple licensors of top-fired designs, KBR, UDA, and obviously a huge number of bottom-fired, so vertical cylindrical heaters out there. So when we talk about combustion and tube wall temperatures, we're really talking about all of the different designs of steam methane reformer. They've all got their own little quirks. They've all got specific considerations, but we're kind of talking quite generally today about the impact of changes in combustion and how that, from my side, affects the tube wall temperatures.
Thank you, James. And so as we do deep dive, we're going to focus specifically on the steam methane reformer. And there's really two principles that I want to highlight in this specific presentation. The first one is combustion optimization, and we'll go through what it is in just a moment, and then also tube wall temperature monitoring and how that applies to how both of these combined apply to safety and efficiency of the steam methane reforming process. Now, if we look specifically at combustion optimization, combustion by itself, just as a quick overview, requires three things. The fire triangle says we need oxygen, fuel, and heat in order to make a flame. Now, because of inevitable circumstances of reality, poor mixing or malfunctioning burners or variable fuels, you're going to get some amount of incomplete combustion in the form of what we call combustibles. And at a very high simplistic level, combustibles are effectively carbon monoxide and hydrogen. And so when we think about relevant combustion measurements, it really becomes what's the excess oxygen at the very end, exiting the furnace. We can use that as a combustion control set point. There's also combustibles, which we can monitor for safety and optimization. We'll get to that in a few later slides as well. There's also methane. If there's any fuel leaks, you can detect leaks up front, and then sample flow, making sure that you have an accurate representation of the process. If you're going to be making combustion measurements, you should also make sure that you have an accurate representation of the process. So that's just at a quick high level. But when we go a little bit closer and look at this combustion process, there's really different ways of operating. Now, stoichiometric is a fun long word, but really what it means is the exact one-to-one mixture, the perfect one-to-one mixture of fuel and oxygen to produce exactly the exact amount of carbon dioxide and water, creating the maximum efficiency, maximum heat transfer with the least amount of heat loss. Now notice in stoichiometric combustion that there is no excess of oxygen in perfect conditions. There's just no extra oxygen on the flue gas. If you did an excess oxygen measurement, you'd see 0 on the outlet. Now, in the real world, we tend to operate a little bit excess oxygen in the flue gas, a little bit excess air at the burner. And that's typical, and what that allows you to do is it's a little bit less efficient, and it generates a little bit of carbon monoxide and hydrogen, a little bit of low levels of combustibles, but it's safer because you don't have any risks of explosions, you don't have an unsafe condition. Now, notice that there's a slight amount of excess oxygen in the flue gas that you can see right here that gives you a little bit of safety margin to make sure you're operating safely. Now, a potentially dangerous scenario would be a fuel-rich condition or an oxygen-deficient scenario where you don't have enough oxygen. You have too much fuel but not enough air at the burner. what happens is you operate much less efficiently. So it's very inefficient because you have a whole bunch of unburnt fuel going out the stack and in partially oxidized fuel in the form of carbon monoxide and hydrogen. So extremely high combustible levels, but it's also a unsafe condition. And notice that there is no excess oxygen in fuel-rich conditions. So when I say excess oxygen, there's no excess. There's no excess oxygen exiting the stack. So just from the standpoint of an excess oxygen measurement and combustion optimization, let's talk about that for a second. So when you look at natural gas, and this applies to a lot of different hydrocarbons, I just present, and I've run the calculations for hydrocarbons outside of natural gas, but if you look at just like methane, for example, there's a correlation between the excess oxygen in the flue gas at the stack, exiting and exhausting from into atmosphere, versus the excess air at the burner. So how much air are you directing at the burner? And it's a pretty linear correlation. And the one thing I want to point out is if you look at 3% oxygen, so 3% oxygen in the flue gas exiting the stack, that's roughly correlated to about 20% excess air at the burner. So 3% excess oxygen in the flue gas, roughly 20% excess air at the burner. You have some safety margin before you get to stoichiometric conditions down here. Now the same is true for 2%. If you have 2% excess oxygen, you have about 12% excess air at the burner, less safety margin, but you have a window where operating between, again, this is for illustrative purposes, but for natural gas, generally between 2 and 3%, you have a safety margin, correlated safety margin of about 12 to 20% excess air at the burner. So why do I point this out? Well, this is excess oxygen in the flue gas or excess oxygen in the stack measured by a combustion analyzer. And this is excess air at the burner. So I presented to you this slide on an excess oxygen scenario, and this represents 20% excess air at the burner, 20% excess air at the burner, and corresponds to an excess of 3% oxygen in the flue gas, so exiting the stack. So I just wanted to make the correlation one-to-one apparent. Now, if you look at the efficiency losses of excess air, so I already said that the typical operating set point might be 2% for natural gas, and that correlates roughly to about 12% excess air at the burner. James, is there anything you wanted to mention before I go any further?
No, I'm okay, Tim. I'll raise my points during the section on TWTs because I've got a few points about how this relates to increases in process temperature.
Oh yeah. This is that's where it all comes together. So yeah, I appreciate you pointing that out. So yeah, as we think about this, we'll also I'll mention the impact on 2 well temperature. Yeah, I appreciate that, James. So at a typical operating set point, again, this is for illustrative purposes, but at about 2% excess oxygen, you have that about 12% excess air at the burner safety margin. And that 2% really represents some amount of carbon dioxide emissions and some amount of NOx emissions. Now, as you go higher to say closer to 3% excess oxygen, you're actually increasing your carbon dioxide emissions and your NOx emissions. Now, why is that? Really, it's because there's a higher fuel consumption. You're burning more fuel at 3% excess oxygen, and that directly increases your amount of increasing more fuel, which means you're increasing your carbon dioxide emissions, which also translates to more NOx emissions at the burner. And then if you go higher to say closer to 4%, you have even higher carbon dioxide emissions, even higher NOx emissions. So for all intents and purposes, this correlation also relates to the efficiency losses. You become more and more inefficient as you increase your excess oxygen set point. And again, that's because higher emissions driven from higher fuel consumption. So higher fuel consumption creating higher emissions. And just, again, higher CO2 emissions, higher NOx emissions because of higher fuel usage. And we'll just call this, for all intents and purposes, excess air losses. So this is our excess air losses this is just our excess air losses graph, if you will. So this is excess oxygen. Well, what about combustibles? So if we represent combustibles as the red line, so combustibles and measure on this side, what you'll notice is that as you increase excess air or excess oxygen in the flue gas, your combustibles go way down, which is good. You're getting more out of you have more air available at the burner, more is being reacted, so you have less incomplete combustion, also known as combustibles. But you'll also notice that as you decrease your excess oxygen, you have this massive spike, and what we call that is combustibles breakthrough, where after a certain point, it becomes a very unsafe condition with a lot of combustibles exiting the stack. Now, we don't want that, and so we want to monitor before that. But because it becomes more and more inefficient as you increase your combustibles. Now, from that standpoint, let's look again at the excess air, and let's overlay the two. Now, we talked about the 2% being a typical operating set point. But when you measure both excess oxygen and combustibles together, you find that there's an optimum control set point. And that optimum point has enough safety away from the combustibles breakthrough, but it's also less excess oxygen that would increase your fuel consumption, your carbon dioxide emissions, your fuel usage. So ultimately, by measuring excess oxygen by itself, you have an operating set point. By measuring combustibles, again, this carbon monoxide, hydrogen, you minimize your efficiency losses, and you have a mechanism for optimization. That's what we call, combustion optimization, and how it reduces fuel and emissions, greater efficiency. So again, lower fuel consumption, reduce emissions, and also provides the added benefit of avoiding unsafe conditions by having that high combustible breakthrough point. And now I mentioned that these were the first principle being combustion optimization. This is where, as you decrease your excess oxygen to closer to stoichiometric conditions, you want to monitor for your combustibles. But there is a green window in the middle. And just as a quick highlight, the Thermox WG5 combustion analyzer is something that measures excess oxygen, combustibles, and hydrocarbons, including methane, ethane, and other hydrocarbons. Now, I wanted to point this out because it supports the decarbonization of steam methane reformers by monitoring for optimized combustion, reducing fuel consumption by having these excess oxygen and combustibles measurements, also through safe monitoring of combustibles, again, through combustible measurements as well as hydrocarbon measurements to monitor for fuel leaks. It's also designed with enough redundancies and diagnostics for SIL safety systems. The excess oxygen was SIL 2 capable certified, and we recently got the RTD combustibles detector certified for SIL 2 as well. So an added benefit for safety systems in your interlocks and for your safety instrumented functions. And beyond that, it also has the added benefit of providing fast responses for closed loop extracted design. So you mount it right to the process flange, and that provides a way to have fast responses on the process. Now, that being said, it's certainly an AMETEK solution that I want to highlight to decarbonize steam methane reforming combustion processes. Okay, any questions so far, John?
None so far, Tim.
Okay. All right. Now, that was basically focusing on so again, we go back to the steam methane reforming process, as I mentioned. We talked about combustion optimization, but now let's talk about the two-ball temperature monitoring. So there is a correlation.
Tim, we did get one question just come in.
Sure.
Question is, if you were only to combust hydrogen as part of a decarbonization initiatives, how would you test for a combustible atmosphere in the absence of a carbon molecule?
Great. That's a great question. I'll go back for 1 second. So combustibles. So again, hydrogen is so that's a great question. Hydrogen is a fast-moving molecule. It's very reactive. If there was any unburnt hydrogen present because of poor mixing or because of even diffusion, even it's just buoyancy, you would be able to use a combustibles measurement to monitor for hydrogen. So to sort of answer your question, you can still test for combustibles by monitoring with a combustibles measurement, because hydrogen is still visible. And that if you even, and also, I don't typically talk about it, but the hydrocarbons detector, the methane detector, can also be used to detect hydrogen because it's similarly reactive. So how can you use it to test in the absence of a carbon molecule? You would have the ability to still use the combustibles detector for ppm level measurements of hydrogen, and then also the hydrocarbons detector for percent levels of hydrocarbon methane, but also in the absence of a carbon molecule, you can also use the hydrocarbons detector to monitor for high levels, percent levels of hydrogen.
Tim, it's worth saying as well. I don't think we've got any evidence of this, because I don't know any 100% hydrogen firing SMRs, but there's still methane in the tubes themselves, and there's still combustibles in the tube. So I'd be interested to see what your analyzer would do in the case of a tube leak. It would probably be a very rapid detection method of seeing if a process tube has started to leak, because you'd start to see methane where you wouldn't expect to see methane.
Yeah, and that's a great point, James, and that's partly why I recommend the hydrocarbons detector to monitor for fuel leaks and high spikes of hydrocarbons or even hydrogen. For that reason, just monitor for tube leaks like that. Yeah, great question. Thank you, John. All right, so just going back to, as I was saying before, so if we zoom out and we talk about the Steam Methane Reformer, and we talk about how does combustion optimization and tube wall temperature monitoring kind of go hand in hand, that's really where these principles kind of come together. So we talked about it. We talked about how if you start using combustion optimization to reduce your excess oxygen levels, you start to increase your combustibles level. Now that together, that provides you combustion optimization. You have two measurements that allow you to have efficiency, and also monitoring from combustibles breakthrough for safety. But what happens is as you leverage combustion optimization, you also have an immediate increase in the tube wall temperature. As you lower your excess oxygen, you're also burning hotter. And because you're burning hotter, you have to monitor for the integrity of your tubes and the tube walls to make sure that you don't have leaks, and also to make sure that you don't have hot spots or any of those items. Anything else you want to share on that, James, before you do the deep dive on the connection between the two?
No, I think that's the fundamental relationship, and it's born out of experience. As we see the excess oxygen levels go down, you do see more issues with highly local excess tube temperatures and hot bands where perhaps conditions have accelerated more quickly than they would have in the past. Catalyst degradation or carbon formation on the inside of the tubes has happened maybe more quickly than it has in the past as the excess oxygen goes down. Because as you said, if you change nothing else and just go reduce your excess oxygen levels, your tube temperatures will increase. There was one question. I guess it's better to ask it now, because we'll go on to tube wall temperatures. It was asked in the chat, so I guess it's been missed. But the question was, because I don't know the answer, I'll ask it to you, Tim. Is there a minimum level of oxygen till the analyzer will measure, or does it not require O2 measurement of combustibles? I guess it's asking about the lower range of the oxygen sensor.
Is there a minimum level of oxygen that the analyzer will measure? Yeah, as you decrease the oxygen level to below, I think, 100 ppm, we do an automatic automatic trigger of high combustibles, high carbon monoxide, or high combustibles and high hydrocarbons. And that's partly because that's partly because with low levels of oxygen, you need a certain amount of oxygen present for the combustibles measurement. So we immediately trigger at unsafe conditions, at low oxygen levels, closer to stoichiometric, we trigger high combustibles and high hydrocarbons alarm. So I hope that answers your question. And then I see there's another message in the chat. So can we replace the existing natural gas with hydrogen as fuel gas without any modifications to setup? I actually did another webinar on this. The short answer, there may be a couple little measurements, little changes that you'd have to look at around the burner. I could also forward it. I'd recommend that you check out our AMETEK Process Instruments YouTube channel around modifications of the burner in order to fire hydrogen. There's a couple little things you'd have to do, but surprisingly, a lot of burners are suitable for it. All right, so good questions there. Before I turn it over to James to talk about it, I do want to point out one other thing. I mentioned how stoichiometric conditions has highest efficiency, highest heat release. Well, what is stoichiometric conditions but at this jagged line of excess oxygen? And so as a result, it has the highest maximum efficiency. It also has the highest temperatures. So inherently, there is a correlation between, as you lower, in addition to James's experience seeing this, as you lower the excess oxygen, you certainly increase temperatures. As you increase excess oxygen, you have more and more inerts in the system, more nitrogen from the air, more oxygen to heat. All those inerts lower your temperature because they're inert, they're not actively reacting. But as you get closer to lower levels of excess oxygen, you have maximum heat release. You also have maximum temperatures. So that's a part of the chemistry behind what's driving these measurements. So that being said, I'm going to pass it over to James to do a deep dive on tube wall temperature monitoring.
That's great. Thank you very much, Tim. So Tim and I are always trying to figure out how do we connect the dots between the combustion side, which AMETEK Process Instruments are experts in, and then the temperature side, which we're experts in. So the kind of keywords that I've written down are when it comes down to temperature, what are we really looking for to help get those additional gains that we're looking for? And it's really comes down to accuracy, efficiency, process optimization, and then balance or uniformity. So I'll talk about a few of those things over the next 10 or 15 minutes, and then we'll open up to questions as well. So in terms of temperature processes, we work in the near and mid-wave infrared band. So we are focusing on non-contact infrared temperature measurement. One of the nice things about that with the near infrared and the mid-wave infrared of the electromagnetic spectrum is the wide temperature range that you can cover. So you can cover from 300 to 1300 degrees C or 570 to 2400 F in a single instrument in many cases. The experience that we have teaches us that proper data correction is critical. If you're measuring inaccurately high, so if you've got a reading which is false on the high side, so you're reading 950, but really you're 900 C, for example, what you're going to have is high methane slip, so increased emissions, not helping our carbon intensities, not supporting our decarbonisation objectives. You'll have margin loss via low plant yield, so you're running at a lower load than you would typically run at. And you'll be chasing false alarms. So they're kind of ghost alarms that the plant thinks are critical and serious, but really you're operating a lot colder than you thought you were. And we see that probably more than customers running on the inaccurate low side. So despite what Tim said about, reducing set points, increasing temperatures, what we see a lot of the time is some kind of paranoia that when people have reduced those oxygen set points, and there's more of an attention on temperature, that a lot of people will misinterpret the data and have these errors which cause false alarms versus more serious alarms. The more serious type of inaccuracy is on the low side. So if you're measuring 850, but you're really running at 900 C, then you will potentially have safety issues caused by tube ruptures, or even worse, tube collapses. You will lose reliability because of those upsets or incidents. You'll lose margin because of those reliabilities. And the chart on the right shows you what happens if you do run over temperature. So that's switching to F. If you run over 1850 degrees F on a tube wall temperature, the lifetime of that tube really rapidly diminishes. So we need to operate in that window where we're not chasing false alarms and we're not worried that we're about to melt the reformer, but that we're also not we're not reducing our tube lifetime. I visited customers where people get 15 or 20 years lifetime from their tubes, and if that was on a site where the load could be increased or there was a demand for additional yield, then that's missed profit essentially. Oh, I'll go back one slide. Could you just take that back one slide, Tim? There you go. Thank you. So one thing that we see which shows itself as a temperature phenomena is carbon formation on the inside of a tube. So that's generally when you've got a low steam to carbon ratio, i.e. you're running a rich process gas. So you have heavy hydrocarbon in your feedstock. That's occurring more and more often as many gas wells approach the end of their useful life. What happens then when you have that real rich gas is that the rich gas mixture, the catalyst activity drops. So the inside tube wall and the process gas temperature increases. So the carbon formation exceeds the carbon gasification rate. So we're getting solid graphite essentially form on the inside of that wall. So that's a typical coking process. So that could be caused by issues with the catalyst or loading. It could be caused by the insufficient purging of the residual hydrocarbons prior to the restart, or it could be caused by complete loss of steam. So, I'm on a delay here.
After what happens. Sorry about that.
We'll go back one.
Back one. Okay. Yeah. Sorry about that.
No, it's okay. There's a slight delay on my click. So one of the consequences of that is you get a runaway reaction where whereby the heat transfer from that hot furnace atmosphere to the relatively colder process gas reduces. So you end up getting hot spots on the surface. The hotter that surface gets, the more likely the tube is to creep. The more creep, the more likely it is to rupture, and the more likely you are to get a leak. The more likely you are to have a leak in one tube. Once that tube's nipped, that tube then becomes a radiant tube, which radiates heat onto adjacent tubes. So you can have a kind of runaway reaction that starts with a small local hotspot, but becomes a hot band, or it becomes a set of tubes that need to be nipped. So what we typically do with customers is find ways to talk about the furnace balance. We look for areas in the furnace where temperatures or temperature limits have been exceeded. So one customer that we did this study with reported a 12 times return on investment, and this was with a partner of ours, Becht, who identified the cost to replace those tubes would have been $80,000, and then there was a $300,000 lost opportunity avoidance if that hydrogen would not have been available for the hydrotreaters. And then we work also with the Ammonia Know-How Industry Association, and they identified 22% of equipment failures were caused by issues with the primary syngas reformer. More than 50% of those involved tube wall temperature excursions. So tube wall temperatures are, in a lot of ways, canary in the coal mine. They're a very early warning of a potential issue somewhere in the combustion atmosphere or in the process reaction itself. That's an example of what happens when a tube does eventually fail. So what do we do at AMETEK Land? The traditional method of measuring these tube wall temperatures is like you see in front of you. So that's a handheld instrument operating at multiple wavelengths. Typically, these readings are gathered by hand. So an operator will go around, write down the measurements, record those values, put in those values to a spreadsheet which records a given background temperature, a given emissivity for that area of the furnace, and then a corrected value is ascertained. There's a couple of concepts which are really important and which do impact the corrected value. One is the geometric view factor, which is the amount of radiation being measured by the pyrometer or by the thermal imager you're using is impacted by the geometry of the tube and by the section of the tube which you're measuring. So we need to consider how much of that radiation at the angle of measurement is making its way to the pyrometer, and how much of that measurement is impacted by background radiation. So background radiation is another really important consideration that we need to make. We don't necessarily apply the same background correction settings for all tubes in a reformer. If we do, and we make adjustments to the furnace on those values, what we might start to do is actively create cold areas in our furnace where we actually want to be creating very highly balanced areas. One way we, sorry, got a slight delay. One way we ensure that we're operating with this very high level of accuracy that we want. So we're really trying to make sure that we've got a very valuable reference measurement. One way that we do that is with the Gold Cup pyrometer. So the Gold Cup really eliminates the three things which we know cause a high level of uncertainty in the furnace atmosphere. The first thing is emissivity. We eliminate emissivity with this measurement by the enhancement effects that the gold hemispheric design gives you. So we essentially create a shadow on the surface of that tube, and we, with the gold surface, enhance the emissivity via a number of reflections, and then we transmit that signal back down to a pyrometer. So emissivity enhancement is achieved with the gold hemispheric design. That shadow that we create on the tube also eliminates background radiation at the point of measurement. So that's the second variable that we eliminate. The third thing that we eliminate is the effect of sight path interference. So in between the pyrometer and the tube, typically you have carbon monoxide, carbon dioxide, and water vapor, which actually do impact the readings somewhat. So we can rule out those interferences by the use of the Gold Cup, because it's essentially a 3 meter or 9 foot long water-cooled probe which we hold against the tube surface to get us that very accurate reference measurement. So that's where accuracy comes in, and that's where, if we can be more accurate, we can make decisions on the running of the furnace which will enable us to increase the efficiency and essentially reduce the carbon intensity of the process. I might ask you to progress the slide instead of clicking, Tim. I've got a huge delay when I click. So another tool that we use is the portable thermal imager for surveys and inspection. So we've always had a range of fixed thermal imagers for collecting this tube temperature information, but we added to that portfolio a portable instrument which gives you the ability to go out into the field and collect this huge amount of temperature data with a portable or semi-portable instrument. So we supply a small flow of cooling air to the instrument, up to 300 litres a minute in the very, very worst case scenario on a very hot furnace on a very hot day. And so we developed that to be able to do surveys and inspections whilst keeping the benefit of the borescope. So the borescope itself means that we can put the camera electronics in a housing, but then we can put a series of relay lenses, and the actual lens itself, which is exposed to the furnace atmosphere, is on a 1 foot or 2 foot or 3 foot borescope. So we can see right into the furnace process. We can get temperatures from a huge number of tubes with just a single imager. Go to the next slide, Tim, please. So these are the different implications of different lens options. So you can see our biggest challenge on a steam methane reformer in many cases is what I mentioned before, the geometric view factor. So that's the amount of tube visible to the camera. With a 90-degree lens, which you see on the right side, you see the resolution on tubes further away from the peep door in this case actually goes down. So we have a limited number of pixels on tubes further from the camera. If we have a 44-degree lens, the same view gives us more pixels. So in many cases, we prefer to have a narrower lens, especially on these top-fired reformers with huge number of tubes in a single row. So a narrower lens gets you a smaller scene, but a higher number of pixels in that scene. Sorry, a larger pixel size in that scene. So a larger pixel size means we get better resolution on the tubes further away from the camera. So with these images, and you can see this is on a reformer with a very high hydrogen fuel content. So we have a very nice what we call transmission through that furnace atmosphere. We can get temperatures from nearly any tube, even though there's a combustion atmosphere in between the camera and the tube. So these high hydrogen fuel contents have very nice transmission. We can get temperatures really nicely from a lot of data points. So what we can start to do with that is build a thermal map, or we can build thermal gradients both vertically along the tubes and along multiple planes. So we can start to create these thermal maps of a reformer to see where the furnace is running colder, where it's running hotter, and then we can make adjustments to the combustion system to make sure that we're running at a high balance. The higher balance we run, the less methane slip we have, the better fuel efficiency we have, and overall the better reliability of the tubes we'll have. Next slide, please, Tim.
I want to just comment on this real quick. This is one of my favorite slides, and I know that you've even sent me some additional photos that you've taken recently where it's even clearer. One of my favorite things about this specific slide is you can see the burners, you can see the flame, but you can also see the relative ranges of anticipating hotspots. So we're talking about lowering the exhaustion in the combustion chamber, monitoring for safety. You can detect hotspots and preemptively prevent a type of fuel leak, for example. So just the impact and just being able to visualize it, it's pretty fascinating to see just how clear you can see just all the different tubes in one perspective. And I know that this is just one of the views. There's many other views that you could have. Right.
Yeah, absolutely. And they're actually, these images are taken at a different time. So that, potential small issues with hot bands, like you see, not potentially catastrophic, but pretty high temperatures where those hot bands are. Those are typically quite hard to diagnose issues. But you can see from that image, the flame on the back wall, or there's some slight flame impingement on the wall opposite to the camera. So you can see the flame is pointing relatively evenly between the tube rows. So it's difficult to say whether or not that's flame impingement. But what customers did in this case was a steam decoking. So they could view with the thermal imager the effect of that steam decoking and watch the temperatures come down during that decoking, and then monitor those temperatures over time. With a manual pyrometer, that would be a really intensive, labor-intensive process. So it's much easier to achieve that type of thing with thermal imaging technology. Next slide, Tim.
Okay, and the other thing I'll just mention is that as you operate closer and closer to stoichiometric conditions, you're effectively starving the flame of some oxygen. Flame gets bigger. So you mentioned flame impingement. It's just fascinating to see how you can anticipate flame impingement and be really proactive on that. So just wanted to highlight that as well. All right, I'll pass it back to you.
Thanks, Tim. Yep, I'll hurry up. Don't have so much time left, so I'll whiz through these slides. Like we said, balancing is a really critical term here. We talked about accuracy, efficiency, optimization, uniformity, and balance. So this is how we balance. We divide the furnace up into rows and tubes. We give ourselves temperatures per tube, and we also look at the vertical gradient. On the right-hand side, you can see the vertical temperature gradients of two tubes, so we can compare those tubes and start to look what's happening with the reaction as the gas heats up down those tubes. So once we build these thermal gradients of reformers, we can get benchmark data and then start to make small adjustments to the furnace. Nothing too soon or too sudden, but we can make small adjustments and increase the uniformity of those temperature measurements and really have a quite significant impact on the yield. And then one thing I've talked about recently with a licensor is, if we are increasing the yield, we're almost by definition increasing the efficiency, because even though we may be using the same or slightly more fuel, if we're producing more products, as a percentage of that production, we're using less fuel to achieve that. So increasing the yield does have an effect on our efficiency, even if it's not necessarily have an effect on our fuel pricing or our fuel spending. Next slide, Tim. So these are a couple of examples. If you just play those, Tim, if you just click it forward, it should play those. These are examples where we've used the borescope technology to get into areas of the furnace which are really typically difficult to access. For example, on the left-hand side, that's a hot collector inspection. So we can look at collector temperatures using the borescope technology, even when it's a hot collector on the inside of a furnace. We can inspect those weld temperatures, inspect those subheader temperatures. And then on the right-hand side, it's not a steam methane reformer, but you can visualize it as a side-fired steam methane reformer if you like. We can see a huge number of tubes with a single camera. So as opposed to taking single measurements and writing those down, you can put that camera in, take those measurements, and then go and do the analysis from the warmth or the cool of your control room or office. Next slide. Fixed thermal imaging. So we're using the same borescope that I talked about with the portable one, but this time we're fixing those cameras in the furnace. So on the bottom right-hand side, you'll see how we do that. We weld a standpipe. We cut a small hole in the side of the furnace. I've got decent experience doing that, so it's not as scary to people as it might have once been. And then we essentially install the cameras in places that give us the maximum coverage with the smallest number of cameras. So challenges are side-fired reformers. Typically, you need fewer cameras than you do for top-fired. Top-fired, you can need, in some cases, 16 cameras to cover every single row with enough resolution. But we've got quite a bit of experience now in overcoming some of those challenges, and we've worked with most major licensors on that now. And then next slide. This is kind of aspirational. We've got a piece of software called Image Pro Advanced Furnace Monitoring. I think the next step that I want to see happen is how the data is consumed by artificial intelligence, by data scientists, and how this massive temperature data, which is billions of data points, how that's implemented in cloud-based pattern analysis, the closed-loop control systems that licensors are starting to experiment with, and then real-time correction of our models and simulations to make sure that we can spot differences between the ideal state and the state that we're running in. Then we can start to do really smart things with burner control, with tube lifetime predictions, with catalyst lifetime predictions, and with furnace run lengths. So those are just a few of the things that you can do with that temperature data. I've tried to bring a lot of this back to how we can work on yield, efficiency, accuracy, optimization, and balance. And I'll hand back over to Tim to finish the rest of the presentation.
All right, thanks, James. I might call you back a couple more times, but the next couple slides are really just to talk about how we can help. Because I mean, I know we talked about a lot of concepts, a lot of important concepts when it comes to efficiency and to safety, and I just wanted to give you a glimpse of just some AMETEK solutions to consider that we've already talked about today. So as I mentioned in the beginning, the Thermox WG5 combustion analyzer is one solution to give you an operating set point, but also to monitor for combustibles and for hydrocarbons and high hydrogen, if you will, in one device. And as I said, it mounts directly to the process flange above the radiant section, if you will, of the heater to make sure that you get fast responses. And there's we have a lot of different configurations, and that mounts to the process flange, and also that mount remotely as you see fit to support real-time combustion control and safety. And as I've said, you can leverage it for fuel efficiency, for reduced emissions through combustion optimization. And as I mentioned, we're still 2 certified for excess oxygen and for the RTD detector combustible measurement. So there's design for the still combustible for redundancies and proactive diagnostics for burner management systems that require some type of safety instrumented function and safety instrumented system. I'll pass it over to James for the NIRB.
Yeah, thanks, Tim. So I talked about a lot of this technology. There's essentially the camera technology that we use in either the portable or the fixed borescope. So we use near infrared borescopes, that's the NIRB, mid-wave infrared borescopes, that's the MWIRB. We have standard resolution imagers with hazardous area certification, high resolution thermal imagers without, but soon to have those hazardous area certifications. Then we can cover the whole temperature range. We have the Gold Cup pyrometer, which we generally supply to third-party inspection houses, test houses, and to field engineering companies, licensors that really want to get that extra level of accuracy. We have also sold that to end users, but it's typically something that's deployed by service companies. And then on top of that, we do have a ton of software to support all of this technology, and obviously the standard pyrometer applications as well. So, over the years we started just by supplying a single wavelength, single pyrometer to the industry. Over time, we've expanded to the point that we've probably got 12, 13 products which we can supply for steam methane reformers now, including some applications which we didn't even touch on because we wanted to keep this as focused as we could on efficiency.
Thank you, James. And then as we just think through some takeaways that we wanted to share, when you, again, just kind of summarizing, I'll put it all in one place. Some highlights really when it comes to the steam methane reformer and the combustion process around that efficiency, we tend to think about the combustion optimization. How do you lower the excess oxygen safely? How do you, in the process, lowering the excess oxygen reduces the fuel consumption, which reduces carbon emissions. And by leveraging those multiple measurements, you can really tune in to have enough safety margin at the combustion air at the burner, but also optimize that air to fuel ratio. And really comes down to safety, monitoring for complete combustion, for fuel-rich conditions, and for loss of flame or flame-out conditions in fuel leaks. And on the steam methane reforming process side, James, if you want to take those two.
Yeah, of course, Tim. So, like I said, if we can balance the tube wall temperatures, if we can decrease that spread of temperatures, we can increase the feed efficiency and increase the product yield. Less methane slip means less wasted gas, essentially. We're monitoring for those increases in tube wall temperatures that affect our heat transfer coefficients. And then on the fuel leak side, on the safety side, we can monitor for those leaks, hotspots. We can look through flames to look at burners, or we can look at the indirect effect of flames on the tube wall temperatures, refractory temperatures. So overall, I think we've got quite a number of things that we can do for both the efficiency and the safety.
Yeah, both inside and out. And really, it's I think really it adds a very big picture of safety and efficiency to support a steam methane reformer. Hence this presentation. I think when it comes down to other takeaways, as I mentioned, governments and corporations are reducing their greenhouse emissions, and that being said, combustion still remains important. So thinking through hydrogen, is certainly going to be the fuel of the future, a low emission fuel of the future, and steam methane reformers are the essential backbone for driving us towards that hydrogen economy. Combustion optimization, again, through lowering excess oxygen levels to lower fuel to reduce carbon dioxide emissions while monitoring for safety. As James mentioned, really accurate thermal imaging of tube wall temperatures to ensure no hotspots, potential rupture points, and ensure uptime and safety. And really, as I mentioned, like a combined understanding of gas analysis and tube wall temperature monitoring and tube wall temperature data can really improve the balance and efficiency in combustion safety. So anything you want to add to that, James?
No, I think that's it, Tim. Just wanted to thank you really for obviously the opportunity to co-present and the work that you've done to kind of connect these dots, as we say, to make sure our end users understand how they can get the value from both systems working together.
I appreciate your support too, and I think it's a big message, that something that we can really think about for safety. So I appreciate your support on that, James. As we look ahead, I know we're a little bit low on time, but if there's any questions, feel free to put them in the chat or the Q&A, and we'll continue to monitor the chat and the Q&A.
I get I get one question quite a bit, Tim, which is how does hydrogen firing affect the thermal imaging? And it actually makes it even easier for us, because those steam methane reformers that already use a high hydrogen fuel content have given us an insight into that. So the spectral response of the furnace does change, but it actually makes the temperature readings even slightly more accurate.
Yeah, and also just on the combustion side of things, I mean, we can also, even hydrogen firing for combustion analyzer, it's more reactive. We can actually detect it even faster as well. We detect it even more so because of its high sensitivity. Right, great question, James. Or then just as we tie up, I just wanted to, this is sort of our business card, if you will. So feel free to reach out to us via email or over the phone. This is our respective numbers. And then just one thing I wanted to highlight, if you want more information, James and I actually co-presented a article in the Global Hydrogen Review in the most recent article, spring 2023, on safety decarbonization of combustion, highlighting a lot of the points we talked about today in this webinar. But if you're interested, feel free to check out the Global Hydrogen Review. And with that, we thank you for your time and for attending.
Thank you, everyone.
Thanks for your support, James.
Thank you, Tim and James, for the great presentation. I did put a couple of links in the chat on products and local contacts as well. So if you need that, it's there in the chat. And as I mentioned at the beginning, the session has been recorded, and we will post that on the YouTube page in the next few days. So thank everybody for their time, and hope everyone has a good rest of your day.
Thanks, Tim. Thanks, John. Appreciate it.